So hello everyone. In this video, we are going to solve this integral. So this is a problem from MIT Integration Beat. You might have seen it. So if you want to try it on your own, just pause the video and give it a try. Okay. So let's solve it. So first, let's observe that if this limit sign was not here, then this will be a finite sum. Then the problem will be this. And here we have a finite sum. And whenever we have a finite sum, we can swap it with the integral sign. So let's do it. Okay. So solution. First, what I will do is I will swap these two symbols. So limit n goes to infinity of sum k varies from 1 to n of the integral from 0 to 1 by I will take n common out from here. So it will be n times x square plus k by nx plus 1 dx. Okay. Now I can write it as limit n goes to infinity summation k varies from 1 to n of integral 0 to 1 by n times. Here I will try to complete the square. So I will have x square plus 2 this times x. Then I have to add and subtract k by 2n whole square minus k by 2n whole square then plus 1. And we have dx. So now this will be limit as n goes to infinity summation k from 1 to n integral from 0 to 1 by n times this will be x plus k by 2n whole square x plus k by 2n whole square plus this 1 minus k by 2n square. Now, and in fact, this n is independent of x, so I can bring it out here, like 1 by n here. So this will be. Now, one thing you might be knowing is that if we have the integral 1 by x square plus a square dx, this is nothing but this is equals to 1 by a tan inverse x by a. Okay, this integral, and of course we have a plus c. So this is a standard result. Okay, okay. So now here I will have a limit as n goes to infinity 1 by n and sum k varies from 1 to n of. Now this, by the same analogy, I can write it as 1 by a. A is here 1 by square root of this term. So this will be 1 by the square root of 1 minus k by 2n whole square times this will be this one, and then I have tan inverse of x by a. So x is here basically x plus k by 2n upon under root 1 minus k by 2n whole square. Okay, and the limit will be 0 to 1. Okay, fine. So this will be limit m goes to infinity 1 by a k from 1 to n. So I'll get 1 upon under root 1 minus k by 2n whole square times applicable here I have tan inverse of 1 plus k by 2n upon root 1 minus k by 2n whole square minus tan inverse of k by 2n by root 1 minus k by 2n whole square. Okay. Yeah. Fine. So now this is of the form tan inverse A minus tan inverse B. So I can apply the formula. The formula is tan inverse A minus tan inverse B equals to tan inverse A minus B upon 1 plus AB. So this will be limit as tan goes to infinity 1 by n summation A from 1 to n 1 upon with 1 minus k by 2n whole square times tan inverse A minus B will be 1 by root 1 minus k by 2n whole square divided by 1 plus ab. So 1 plus, uh, this will be 1 plus k by 2n times k by 2n upon, this will be 1 minus k by 2n whole square. Okay. Okay. So now here we can see 1 plus k by 2n, and if we factor it out, it will cancel. So we will be left with this term will cancel out, and here we will left with this 12 and 1 minus k by 2. This will be left. So this will be limit as n goes to infinity 1 by n summation k varies from 1 to n of 1 by root 1 minus k by 2n whole square tan inverse. Uh, this will go up. So this will be root 1 minus k by 2n upon 1 plus k by 2n. Okay, and the denominator it will be 1 only. 1 minus a by 2n and a by 2n, so only 1 will remain. So now we have this. Now here, if I consider a function fx, which is equals to 1 upon root 1 minus x by 2 whole square tan inverse root 1 minus x by 2 upon 1 plus x by 2, then we will notice that this thing inside this summation is nothing but f of k by a. So this is written limit n goes to infinity 1 by n summation a there is no 1 to n f of k by a. And we know this thing is integral from 0 to 1 f of x dx. This comes from the Riemann sum definition of the integral. So now our job is to evaluate this integral. So let me write it here. Our job is to evaluate integral from 0 to 1 fx. Which is this way 1 upon root 1 minus x by 2 whole square tan inverse root 1 minus x by 2 on 1 plus x by 2. Okay, so here if I let x by 2 equals to cos theta, then dx will be 2 minus sin theta d theta. So replacing here, I will get this is nothing but the integral. Now when x equals to 0, theta equals to pi by 2. When x equals to 1, so theta equals to cos inverse of 1 by 2, which is pi by 2, and it will be 1 by root 1 minus cos square theta, which is 1 by sin theta tan inverse of under root 1 minus cos theta by 1 plus cos theta times minus sin theta by theta. So this and this will cancel out. So we are left with this negative sign will switch the upper and lower limit. I will have 2 times into 1 pi by 3, pi by 2 tan inverse. Now 1 minus cos theta is 2 sin square theta by 2, and this is 2 sin cos square theta by 2. So this will be tan theta by 2. This will be 2 times integral pi by 3 to pi by 2. Tan inverse of tan theta by 2 is theta by 2 d theta obviously. So this will be theta square by 2 from pi by 3 pi by 2. So this will be 1 by 2 times pi square by 4 minus pi square by 9 is equals to 5 pi square by 72. So answer to this problem here is 5 pi square by 70.